All right, so organic chemistry is way different than general chemistry. Organic chemistry, we really only deal with a small segment of the periodic table, right? Does anybody know which segment of the periodic table, like which direction?
Upper right.
Upper right. So really, if we look at it, it's like carbon, nitrogen, oxygen, the halogens, sometimes sulfur, but really we deal with only a handful of elements. The history of organic chemistry is pretty fascinating, though. So prior to 1830, the definition was completely different to what it is now. So prior to 1830, they thought that organic chemistry meant that it was something derived from a vital source. So what do you think a vital source means? Living, right? So they thought organic molecules were molecules derived from a living organism, right? That's not always true, right? Organic molecules don't have to be derived from a living organism. And this was found out in 1930 when a chemist named Friedrich Wöhler took ammonium cyanate, which is actually a salt, and he was able to turn it into urea, which is an organic molecule that we know is derived from living things. So that kind of threw the whole chemistry world on its head, but chemistry doesn't necessarily have to do with living versus non-living. So they threw that out the window, and does anybody know what the more modern definition is of organic chemistry? There's one element that stands out.
Carbon.
Carbon, right? So it's carbon-based chemistry today. And I know I'm biased, but carbon is the best element. Does anybody know why carbon is so cool? It's a building block, yeah? So let's do a list of why is carbon special. It's a good building block. Why is it a good building block?
4 valence electrons.
4 valence electrons. So it can form 4 bonds. Form 4 bonds. What type of bonds does it typically form? Ionic or covalent?
Covalent.
Covalent. So it usually forms covalent bonds. Going back to the building block idea, what important building blocks does carbon make up? Think about your body. We've got some essential biomolecules. Not everybody all at once. Got proteins, right? What's another one? DNA, RNA, carbohydrates. It's responsible for the backbone of pretty much all our important biomolecules, right? So it's important for biochemistry. So it's really important for biochemistry. What other fields is organic chemistry important for outside of biochemistry?
Nanotechnology.
Nanotechnology, definitely. So material science, I would even go as far to say that. So it doesn't have to be a biomolecule. It might be a solar panel, but it's made up of organic molecules, right? There's also polymer chemistry. That's a huge branch of organic chemistry. Polymer chemistry is the chemistry of plastics. So I know a lot of you are interested in things like that, and we actually will cover polymer chemistry a little bit later on in the year. So carbon is really unique. There aren't a lot of atoms that have this wide diversity of functions and capabilities, right? So let's talk about the history a little bit more. So I wanted to show you a picture of the most unlucky chemist to ever live. This is Gilbert Lewis. Does anybody know what he was responsible for? Lewis dot structures, right? So most of you guys have done those, right? So he was arguably the father of organic chemistry. He did Lewis acids and bases, Lewis dot structures, even went so far as to be the first person to accurately define a covalent bond, but never won a Nobel Prize and ended up committing suicide kind of in shame. So, if you ever feel crummy, you could say, at least I'm not Gilbert Lewis. So the most important discovery, in my opinion, was he was the first to describe a covalent bond. What is a covalent bond? How would we define it as chemists?
When two electrons are shared.
Yeah, when two electrons are shared. What's an ionic bond? That's the opposite. It's not when you share, it's when you take away or transfer an electron, right? So he was the first to describe these bonds where you have two shared electrons between atoms. Where two electrons, and I abbreviate electrons E minus, are shared. Specifically, there's a type of an electron that typically is involved in covalent bonds. What types of electrons do the covalent bond in? Valence electrons. What are valence electrons? Yeah, they're the electrons that are highest in energy or the outermost shell, right? So we'll keep this super duper simple, and we'll do a review of valence electrons. All right, so they're the outermost or highest energy electrons. So let's take hydrogen, symbol H. How many valence electrons? 1. So we just do a dot for the Lewis dot structure. All right, what about carbon again? 4. So if we're trying to do the Lewis symbol for carbon, should I go 1, 2, 3, 4? No. Should I go 1, 2, 3, 4? No. What should I do? 1 on each side. So if you remember going back to Gen Chem, start out with dots going around and then pair them up after you've got all 4 sides covered, right? What about boron? B. So it's 3. So we go 1, 2, 3. The easiest way to remember valence electrons is to take a look at the periodic table over there and look at the Roman numeral, right? So hydrogen is in group 1A, 1 valence electron. Boron's in group 3A, 3 valence electrons. Carbon's in group 4A, so 4 valence electrons. If you're ever in doubt, just look at the periodic table. After a while, though, it kind of becomes intuitive the more we do these sorts of drawings. Electrons are kind of funny, though. Electrons tend to be paired. Does anybody know why? What special property do electrons have?
They have lone pairs.
So electrons can be a lone pair, but electrons also have a state called spin up and spin down. And in order for them to be stable, they usually want to pair with something, another electron of the opposite spin. So we typically see them paired. However, not always. Sometimes you will see unpaired electrons, and we'll talk about that a little later. And we've got covalent bonds as one type of pairing. And then you mentioned before lone pairs are another type of pairing. So lone pairs are where they just kind of hang out on the side of a molecule, but they don't actually get shared between two different atoms. So let's take a look at Lewis dot structures, and I'll teach you guys my rough and dirty Lewis dot structure methodology. I know you may have been taught a little bit differently in your general chemistry course, so if you feel confident with how you draw it already, you're welcome to use that system. But there are some key things. First one is electrons tend to be paired. Like I just said, so try to avoid drawing single electrons. That doesn't really occur very often. And then atoms prefer how many electrons around them? Yeah. I know in general chemistry textbooks they call this the Octet Rule. I don't like calling it a rule because I'm sure as you guys saw in general chemistry, there are a ton of exceptions, and that can be really infuriating to have a rule with a million exceptions. So I just say they prefer to have 8 electrons. More often than not, you'll see 8 electrons around a central atom. All right, and then the other thing that's really important is you want to include formal charges on appropriate atoms. And there's a really simple thing you can do to determine formal charge. You can take the valence number, then subtract your lone pair electrons, minus half of your bonding electrons. We don't count them all because they're shared between 2 atoms, so only count half of those. So let's take an example here. So we're going to do HO minus. Does anybody remember what that's called? Hydroxide, right? It's our common base that we saw last year in or general chemistry. So let's do this.
Can you go up for a second?
Oh, yeah.
What does that say after valence? Is that just a pound sign?
Valence number.
Valence number, yeah, pound sign. Sorry, sometimes I do shorthand. Hashtag. You can Twitter it. All right, so let's do this. So first thing I do is I draw my first atom, hydrogen. It's got 1 valence electron because it's in group 1A, so I put 1 dot next to it. And then oxygen, right? How many valence electrons does oxygen have? 6. So I'll go 1, 2, 3, 4, 5, 6. And then what we need to do is we need to try to pair up these electrons. So what I like to do is just circle them. I'll say, all right, these 2 can be paired. And then what about this guy over here? How will we pair that one up? We can't really. However, if we look over here, we've got a negative sign, which means that there's 1 electron being added into the system. So what I'm going to do here is I'm just going to say, all right, we've got an electron that's getting pushed over here so that we end up with a new lone pair. So if we end up drawing hydroxide, we can draw this covalent bond, the shared electrons, as a solid line. Then we have oxygen. Then we've got a lone pair here, an electron there that is now paired with that blue electron that was added. So I'm just going to draw it as a blue color so we can keep track of it. All right. If we look here, we still need to include a charge. Where does the charge go? On the oxygen, because it's the atom that gained the electron, right? So oftentimes what I do when I show charge is I'll show it and then I'll put a circle around it. That way we don't get it confused with a bond or anything else. So this is HO negative with that electron that was added in. Let's do another one. All right, the next one we've got NH4, and I'm going to put a plus up here. So I'll give you guys a minute to do this, but try to do the same strategy where you draw nitrogen with its valence electrons and then draw 4 hydrogens with their valence electrons and try to get them linked up. Once you think you got it, put your hand up so I can kind of gauge the class. All right, show of hands again, nice and high. All right, it looks like we're almost there. So nitrogen has how many valence electrons? 5. So I'll go 1, 2, 3, 4, 5. We've got 4 hydrogens. Each of those have 1 like we just had. I'm going to put it equally around it. And then like before, I'm going to circle these. I'm going to say, well, we like to have paired electrons, so I'm going to pair that one. I'm going to pair those two, pair those two, pair those two, and actually I'm going to move this electron over a smidge. All right, so now we're in kind of this weird position, though. Nitrogen has 8 electrons around it that are participating in covalent bonds. What about this electron, though? What should we do with it? Get rid of it, right? So we're just going to say remove this electron. So in the first example, we added an electron in, which is why that oxygen had a negative charge. But in this case, we're pulling an electron away from nitrogen, which means that nitrogen will have a positive charge. So when we go ahead and we put this together, we've got NH4, where nitrogen now has a positive charge. One thing I've seen a lot with students coming from general chemistry is instead of drawing it like that, they'll say like this. Did some of your general chemistry instructors do it that way? I see it occasionally. You see this in inorganic chemistry a lot, which that little bracket with the plus sign means the overall molecule or ion has that specific charge, right? In organic chemistry, I really prefer for you to put the charge on the specific atom that has the charge. That way we know the positive charge is on the nitrogen, not on a hydrogen or anything else, right? So please, I'll just put worse and better. Please try to do it where you draw the positive charge on the correct atom. All right, let's do one more before we leave. I know you guys are like, this is the first day. What is he doing?
Quick question on that last one. So
Yeah.
the whole ammonium doesn't have the charge, just the nitrogen?
So it's not that the one on the right's wrong. It's just it's more accurate to show the positive charge on the specific atom where it resides. So I preferred for you to draw it the way on the left, if that makes sense. All right, one last one. Let's do COCl2. What tends to be the central atom, carbon, oxygen, or chlorine? Carbon. Carbon likes to be in the middle of things. So we'll do this. Put carbon in the center. Whoop. Carbon's got 4 valence electrons, so I'll go 1, 2, 3, 4. I'll do the chlorines down here. So Cl, Cl. How many valence electrons for chlorine? 7. So group 7A. 1, 2, 3, 4, 5, 6, 7. Okay, so now we're in good shape, right? This chlorine can pair up with those electrons. All right, and then we've got oxygen. How many valence electrons for oxygen? 6. 1, 2, 3, 4, 5, 6. It's in group 6A. So what do you think we should do with the oxygen and carbon? Double bond, right? So we aren't just limited to single bonds. If you can pair up multiple electrons, you can. So when we draw this out, let's try to kind of clean it up a little. You can have a double bond to oxygen. That oxygen still has 2 lone pairs on it, so I'll draw those in. And then the carbon's also got single bonds to 2 different chlorine atoms, so I'll draw those out here. And each chlorine has 3 sets of lone pair atoms. This molecule is called Phosgene. Phosgene was one of the first chemical weapons used in World War II. It's pretty nasty stuff. If you breathe it in, it will actually react with the water in your lungs to produce hydrochloric acid. If you have hydrochloric acid on the inside of your lungs, it will actually blister your lungs. So if any of you get a chance, I would recommend going on YouTube and reading or watching the World War I channel. They do an episode per week of World War I, and the ones on chemical weapons are fascinating and horrifying at the same time. So we'll talk more about some of these funky molecules, but what I want you to do tonight is to practice Lewis dot structures. Make sure you grab a pod, and it needs to be handed in at the start of class tomorrow. If you have any questions, email me or stop by my office. If you have Monday lab, make sure you meet me upstairs right after lab, outside the lab room.